Hello everyone. Today let's discuss an important problem in Leetcode, that is the critical connections in a network problem. So what it's going to what this problem is that it is based off an important algorithm in graph theory known as the Trajan's algorithm. So Trajan's algorithm is used to find out critical connections as well as articulation points in a graph. So what is a critical edge? Well, a critical edge is that edge which when removed will make the graph into two disjoint graphs. So when you remove the edge between 1 and 3, we are going to get this 1 2 0 graph and this 3 graph which are disjoint. So this is a critical edge. Now what are articulation points? Well, any vertex which along with all the edges connected to that vertex when removed will create two disjoint graphs. So one is an articulation point because if you remove all the edges as well as one from here, you'll get 3 0 and 3 graph and the graph containing 2 and 0. So for today's video, let's try to use Trajan's algorithm to find out the critical connections in a graph. So what Trajan's algorithm does is it does a DFS, a depth first search. So also it keep tracks of two quantities when doing this depth first search. That is the visiting time, which is the time the at which it visited each of the vertex in the DFS. Also it keeps track of another quantity called load time, which is used to figure out whether there was a back edge in the path that the DFS currently explored. This is important because it can give us whether edge is a critical edge or not. So let me try to walk you through an example so you get a better idea of how Trajan's algorithm works. So initially we are going to have both the visiting time and the load time to be the same. So let's start exploring our DFS from node 0. We have the visiting time 0, load time is 0 itself, and then let's explore node number 1. The visiting time is 1, load time is 1. Then let's say we explore 2. So we have the visiting time as 2 and the load time is going to be 2 itself. Now now we have this edge between 2 and 0. So we are currently exploring not finished exploring 0, and we are exploring from 2. So this edge is a back edge. A back edge is an edge that creates a cycle. So this edge creates a cycle, that's why it's called a back edge. Now what should we do in Trajan's algorithm's case when we encounter a back edge? We need to set the load time of the edge of the vertex from which we were coming in a back edge to have the minimum of load time of this edge and the visited time of the neighbor. So we have the visited time of 0 to be 0 and the load time of 2 to be 2. So the load time of 2 is going to be, as per this condition, 0. Okay, so 2 will get load time as 0. Now we have finished exploring children of 2, so we are going to go back to 1. Now deviating from the normal DFS, we need to do an additional step here. That is, if we have load time of the current node lesser than the load time of neighbor we are coming back from in case of a DFS, then that is a critical edge. So let's try if that condition meets here. So the load time of 1 is 1, which is not lesser than the load time of the neighbor from which it's coming from. This is because there was a back edge here, and that's why this condition is not met. Hence this edge is not a back edge. So what you should do in that case? In that case, what you need to do is you need to modify this load time and make it the same as the load time of 2. So we are going to make it as same as 2. Now from 1 we need to again explore 3. So 3 is going to get a visiting time of 3 itself, and load time is initially going to be 3 itself, and there are no more neighbors of 3 that we need to explore, so we can go back. And for 1, let's see if the condition for critical edge is met or not. The load time of 1 is actually 0, and it is actually lesser than the neighbor load time, which is 3 for the node number 3. So we have the edge between 1 and 3 is package, is a critical connection, right? So we have finished exploring all the children of 1. Now we are going to go back to node number 0, and let's see if this condition is met. The load time should be of 0 should be lesser than the load time of 1 for it to be a critical edge, for the connection between 1 and 0 to be critical. So that condition is not met here, because load time of 0 is 0 and 1 is 1, which is same and not lesser than. So yeah, that's the algorithm. Now let's try implementing it. So we have the connections represented as a vector, and n being the total number of vertices in the graph. So let's try to build our graph. So I'm going to make use of the adjacency list representation of the graph, and so let me try to build that. So for int I equal to 0, I less than, so number of edges that we have, which is going to be condition.size, and I plus plus, and so I need an adjacency list. So how am I going to store that? Let me store that using a unordered map of int, and it's a list of int and its adjacency list of our, right. And what do we need to return here? So we need to return a vector of vector, which is essentially all the edges which are critical. So let me also make that here when I do this. So this we have result. Okay, what else we need? So we need to have the visitor time and load time for all our vertices. So let me try to make that too. So we need the vector int visited time, and we need also the load time. It's the same, so we can have something like this. Load time. What else do we need? Well, we need an actual counter for time to keep track of the time in our DFS, and we're gonna initialize it to 0, and that's pretty much whatever we need. So let's try to build our graph. So we need to make our adjacency list. So adjacency list of connections of adjacency list of connections of I 0. So a sample, let's try to have a look at our sample input. Yeah, so there is going to be, it's a pair basically. So connection of I equal to connection of I comma 1. We could have something like this, but sorry, it should be pushback since it's vector. Okay, now since it's a undirected graph, when you form the adjacency list for 1 0 and 0 1, we need to add two edges basically, because it's undirected. So let me just swap them here, and that's it. We have built our adjacency list. Now we need to actually go ahead and do our DFS. So for that we need an ordered map of integer pool to just tell whether our something is visited or not in DFS. This is standard thing that we have for a normal DFS. So we can even have an unordered set here, but I'm just having a bool as a value in an unordered map. This also should work fine. So visited time, yes. So now what we need to do is visited time, we need to resize it because we have n elements, so we need to allocate memory and initialize that memory, and same thing we need to do for load time also. Now what else do we do? What else we need to actually do the Tarjan's this is a spelling, Tarjan's algorithm. Let me try to implement that function. So it returns nothing, and it's a Tarjan's algorithm. And let's see, so what input? One input is going to be our visited map, it's we are gonna use for our DFS. What else we need? We need the current node, right, and we need the parent node from which we came from, because we need to do this condition check. And so let's do that. And what else? Yeah, let's first write down condition required for a simple DFS. So we just do this: visitor of current node becomes true, and if and what else? So yeah, for an int of neighbor in adjacency list of current node, we need to again call the DFS. If it's if we are not visited the neighbor, if we have not visited the neighbor, that's it. Yeah, so this is the standard DFS that we should do. Okay, so let me try to figure out what the argument here should be. Yeah, we are going to pass on the same visited, and the current node is now the neighbor, and wait a minute. Yeah, the parent is going to be the current node. Yeah, so this is a normal DFS I wrote down. In case of Tarjan's algorithm, we have to have the visited and load time as well. So let's try to populate them. Visited time of current node is going to be equal to the load time of current node, which is going to be equal to the counter time plus. Right, so we have our load time and current time set. Now what else? We have the DFS working for us. We need to have all our checks the conditions that I mentioned before now. So what we have is this load time of the current node should be minimum of load time of current node, and sorry, let's first have our load time of neighbor. So what basically we are doing here, so we are doing updates load time of all nodes while traversing back in DFS. Okay, now we also need to check if visited time of current node is lesser than that of load time of the neighbor, then this is basically the condition for a critical condition for a critical edge. Then we have our result, one new result we got, and we can just use the brace initialization, which is supported from C++11, which you can do. Yeah, so that we could do. And yeah, so what if we encounter a packet? So that would be the else case here, because if in one of the neighbors we have a node that we are visited already, that means it's a packet. So it's a back edge. Okay, what we're gonna do here, we are going to put the load time, and I have written down this condition, I think, yeah, this one. We're going to need the load time of the current node to be minimum of load time of current node and the visited time of the neighbor. That's pretty much it. And what else? Yeah, now what else? Am I missing something? No. So we need to populate visited here, and we need to start from node number 0, and let's start our parent to be -1, because no, the starting we don't have any parent. Okay, and yeah, one more condition I missed here is if neighbor equal to parent, we don't have to we can basically continue, otherwise we'll go into a forever loop. Okay, so I think this code should work. One thing that might be required is, since we are using a list here, we may have to include list. I don't know whether Leetcode does it automatically or not, but let's try. Okay, DFS, sorry, the name is Tarjan's. Undeclared identifier load time. Oh, M load time. Okay, M load time and M visited time. Okay, should be working now. Oh right, I didn't return the result. Right. Right, so our test case passed. Let's try running this. Right, all good. So, guys, that pretty much covers Trajan's algorithm. It's one of the most important algorithms in uh, graph theory. Thanks for watching, guys. See you guys on the next one.